Okay, I'm very happy to introduce our very own Florencia Orosz Hunziker. She is the NSF postdoc at University of Denver, and that's her talk. All yours, Flore.
Thank you so much, and thank you all for being here. I'm going to be talking on C-graded vertex algebras and conformal flow. This talk is based on joint work with Katrina and Kari and Veronica and Gail. Let's see if this works. So before we start, let's acknowledge that this is the first talk I ever give after winning a World Cup. So I just want to celebrate such an amazing accomplishment. And once we mention that, which is the first time in my lifetime, even though I've heard a lot about Argentina winning the World Cup before, is the first time in my lifetime that it happens. So I just wanted to bring it up and celebrate with Messi and drinking mate. Such a big accomplishment for Argentinian vertex algebraists. Okay, great. So what's the motivation for studying or thinking about the Weyl vertex algebra? And maybe I'll give some motivation. The Weyl vertex algebra is one of the basic free field algebras, together with the Heisenberg algebra of free bosons, the free fermions and the symplectic fermions, which is a good reason to study these vertex algebras. Conformal flow, which we'll discuss in more detail in a second, but the deformation of the conformal vector has been really instrumental in the study of the triple vertex algebra, in which you start with a Heisenberg algebra, you deform the conformal vector, and then you get the central charge CP1 that you want. And the triplet is important because it was maybe the first C2 and irrational vertex algebra in the literature. And this was studied by Miles and Adamovich. And more recently, in this really cool paper that Robert has, conformal flow was useful to prove that all exceptional, where exceptional means something technical here, the level is admissible, etc. I'm not going to go into details, but they prove that all exceptional W algebras are strongly rational with respect to the thinking conformal vector. And then Robert used that he could change the conformal vector and get another grading to prove this rationality result. Great, so maybe this is some motivation to study Weyl vertex algebras. And here's the plan for the talk. First, we're going to talk about what conformal flow is. We're going to discuss some examples, so the Heisenberg vertex algebra in particular. Then we're going to talk about the Weyl vertex algebra and conformal flow in that setting. And we're going to see that the right context to think about this Weyl vertex algebras once we deform the conformal vector is the context of complex graded vertex algebras. I'm going to try to say complex instead of C because my Z for integer and C for complex sound the same. I'm sorry about that. So if I make it extra confusing, please interrupt me and ask me which one I'm referring to. Okay, so we're going to see that complex graded vertex algebras is the right setting to think about what happens to a Weyl vertex algebra once I deform the conformal vector. And we will use the theory of complex graded vertex algebras to classify all Weyl vertex algebras under conformal flow. And finally, I will make the case that the representation theory of the Weyl vertex algebras changes significantly when we deform the conformal vector. We will see that this is quite different from the free boson from the Heisenberg setting. Great, so let's start with discussing what conformal flow is. So if you're working with a vertex operator algebra with a conformal vector omega, then we all know that that means that we can decompose our vertex algebra in this way. In particular, it's integer graded. Each of this graded components is finite dimensional, and we have some lower boundedness condition. And if we write the vertex operator associated to the conformal vector in this way, we know that this modes gives a representation of the Virasoro algebra, and that AL0 gives us the weight of any homogeneous element in this VOA. Conformal flow is this phenomenon in which you actually end up with a family. For some reason, your vertex algebra admits a family of conformal vectors that depend on a complex parameter mu. And what we are interested in today is thinking what happens if I change this conformal vector. If I change the value of mu, what happens to the vertex algebra structure? So I will say in general, deforming the conformal vector or doing conformal flow to your vertex algebra will mean that you'll probably end up losing the eigenspaces, and maybe we'll have to consider generalized eigenspaces. You will probably lose your integer grading, and you may lose the fact that these spaces are finite dimensional. So I claim, and now I'll make a case today, that we will actually need, in general, to consider complex graded vertex algebras if we decide to conformally flow a VOA. Okay, so let's start with one example, a very famous and well-known example. We're going to grab just an infinite dimensional Lie algebra. That's the Heisenberg Lie algebra. It has generators, a central element z, an xn, one for each integer. Z commutes with everything. In xn and xm almost always commute, except when n is the opposite of n, and in that case, you get n times delta. So in particular, just to warm up, this is 0, but this is not 0. This is 2 times z. Great. And now we can fix a triangular decomposition for H, in which we define the positive part to be this, the 0 part to be this, and the negative part to be this. And now this is a maximal commuting subalgebra, so it has a one-dimensional representation. And we're going to make, so this is just the C1 here, just means a one-dimensional vector space, and I'm going to give it an H greater or equal. So this is a maximal subalgebra that's commutative. I'm going to give it a modular structure for that subalgebra in the following way. Xn is going to just act by 0 for all n greater or equal than 0, while z will act as 1. Great. So now the Fock representation is just the induced module. This was the action that we used to give this one-dimensional vector space in H plus direct sum H0 module structure. And linearly is isomorphic to polynomial ring in this negative variables. And moreover, the Fock representation is a vertex algebra known as the free bosons or the Heisenberg vertex algebra. And maybe this is a nice graphical representation of what this Heisenberg vertex algebra looks like. We have the vacuum, and here at weight 1, we have x minus 1 the vacuum, x minus 1 squared the vacuum, x minus 2, etc. Great. It's a vertex algebra with the following structure. We define y, well, of course, if the vacuum is the identity, but y of this first non-trivial element to be just the power series that contains all of the Heisenberg generators, and we call this field x of z. And then we can define y in any element. This is the basis of the vertex algebra as a vector space. So y in any element of the basis can be defined in the usual way by taking a normal order product of the appropriate derivatives of the field x. And if you like OPE language, in OPE language, there's a free field algebra generated by one field with this OP. And it is well known that it is a vertex operator algebra, not just the vertex algebra, with this conformal vector. So I'm just grabbing 1/2 of this guy, right? But you can already see that there are more people at degree 2. There's another person at degree 2. And it's an interesting question to try to classify all of the Virasoro vectors in the Fock module. And actually, Matsu and Nagatomo did this. They classified all Virasoro vectors and allowed even conformal weight 1 or 0 things in there. But we're not going to focus on that today. We're just going to grab the standard family of conformal vectors in here. It turns out that for any complex number that you choose, omega mu, so 1/2 x minus 1 squared plus mu times this other guy at degree 2 is a conformal vector again. So now we have a VOA that depends on mu. So that's why we're using this notation pi mu. It's a VOA and the center charge changes. So when mu is 0, which is the standard choice of conformal vector, we have the Fock module of center charge 1, but as mu takes on complex values, then the center charge changes. Great. Note that this Fock module, which with whatever conformal vector you choose, is not strongly rational. It has infinitely many irreducible modules, which are given by the Fock modules, one for each complex number, and it admits indecomposable modules that are not simple. And this were classified by Milas. And one can see this from another perspective, from the Jou algebra perspective. So if I go to the Jou algebra, no matter what mu is, the Jou algebra for the Fock module is just isomorphic to the polynomial ring in one variable. The irreducible modules for the Jou algebra are given by irreducible modules for the polynomial ring. And this follows from the work of Frankel and Jou that it will give us the irreducible modules for the vertex operator algebra. And the indecomposable modules can be also obtained by inducing from indecomposable modules for the Jou algebra. So this was studied and explained in work of Milas, in Katrina, van der Werf, in Jingwei. So as I said, inducing from the irreducibles, you're gonna recover the irreducible modules for the FOC module, no matter what your conformal vector is. And inducing with this indecomposables, you're going to end up with indecomposables no matter what the conformal vector is. So in particular, notice that whether the FOC module is rational or not does not change with the choice of conformal vector. And really, the representation theory doesn't change significantly with the choice of conformal vector. Great. Here's another example. The WEYL vertex algebras, also known as beta gamma. And everything in our field has like 4 or 5 names. So maybe other names for this are bosonic ghosts, and there are many more that I'm not even aware of. But I think WEYL and beta gamma is maybe enough names that everyone should be happy. Okay, so we're going to consider an infinite dimensional Lie algebra first. There's a central element K, AM, one for each m in the integers, in A star n, with the following commutator. So AM and A star n is almost always 0, except when n is the opposite of m, and in that case, we want to touch on the central element. Except, notice that there's no, unlike in the Heisenberg case, there's no n in front of this, right? So this is already telling us that A0 and A star 0 are not going to commute, which is different from the situation before. Okay, and then AA is always 0 and A star is always 0. Great. So now we're going to think of the WEYL Lie algebra, and this is the maybe special name for the stock. I think people call it the bosonic ghost Lie algebra and all sorts of things. We're going to call it the WEYL Lie algebra is just the quotient of the universal enveloping algebra of this L by this ideal. So we're just going to have K acting as 1, basically. So now the commutator becomes this. And in particular, as I mentioned, notice that if you were to build a maximal commuting subalgebra, you cannot have A0 and A star 0 because these elements do not commute. So you will have to make a choice. Either you keep A0 or you keep A star 0. Great. We can think of this as some sort of affinization or loop version of the rank 1 WEYL algebra, which is an associative algebra with 2 generators in relations x to the x equals 1. That's the only non-trivial bracket. Okay, great. And maybe, as I said, well, we grab a commuting part, it's just going to be, we're going to fix a triangular decomposition for our Lie algebra L. The 0 part is just going to be the span of the central element, and then the positive part is going to be this space in which we have on purpose excluded A star 0. Because as I said, that's not someone that commutes with A0. Does that make sense so far? We're good? Okay, great. Before we move on, I would like to mention that this WEYL Lie algebra has a distinguished family of automorphisms, the spectral flow automorphisms for each integer. They do this. They're automorphisms of this Lie algebra, and the conjugation automorphisms for any non-zero complex number. We have this automorphisms. They'll be useful later on. And they are definitely useful in the study of the WEYL vertex algebras because we'll discuss this a little more later, but so Simon Wood and Robert Allen, they build a tensor category structured in a certain category of modules, and they did spectral flow of all the simple modules and showed that you needed to spectrally flow all the simple modules to get something that closes under fusion. Okay, great, but that's for later. Okay, so we have our infinite dimensional Lie algebra. We fix a triangular decomposition, and of course, again, we're gonna induce. So we grab a one-dimensional module, and we're gonna give it an L0 plus L plus module structure by making all of the positive, by making K act by 1 and all of the positive part act by 0, as we did before. And the rank 1 WEYL vertex algebra is this induced module. So you may try to represent it as we did before. Oops, sorry. It is a simple module for the WEYL Lie algebra, and it's isomorphic to the polynomial ring in the spirals. Where just as before, we are thinking of all the A negatives, right? A minus 1, A minus 2, but we are thinking of A star 0, A minus 1, A minus 2. So things are a little different than in the Heisenberg case. And on purpose, I would like to notice that n is starting at 0. Great. So if you were to try to represent it graphically, well, this would be a really bad way to represent it. This is incorrect, what's currently in there. But you may naively say, okay, well, I start with a one-dimensional space, and then every time I bring something from L minus, the complement of L0 and L plus, well, I'm hopefully at degree 1 or degree 2. But that's wrong, because obviously we want this -1 to give us degree 1 things, and we want 0 to give us degree 0 things, right? So maybe this would be a more correct representation of this vertex algebra. And that works, except A star 0 is on the top space. It's a degree 0 element. And moreover, all of this are also degree 0 elements. So we end up with an infinite dimensional top space, an infinite dimensional degree 0 space, which tells us this guy is definitely not a vertex operator algebra, since we've lost the finite dimensionality of each graded component. But that's okay. Messi is here to tell us that we can drink some mate and be okay with the fact that we will not get a vertex operator algebra, but we will have a complex graded algebra instead, and that the theory of complex graded algebra, vertex algebras, will help us make sense of what grading we get in this case. Okay, great. So the bi-vertex algebra is this as a vector space, and its vertex algebra structure is given by sending this generator to this field that we're going to call A of Z, this generator to this field that we're going to call A star of Z. And notice that the expansion here is a little different from what we usually use in vertex algebras. And now we can define the vertex operator on any element, because these two generators are enough to give us a basis of the whole vertex algebra. And we define it, of course, as the normal order product of the corresponding scale derivatives of these fields. And it's very easy to see that the Weyl vertex algebra is a simple vertex algebra, and it's strongly generated by these two elements. And notice that when we look at the nth mode of the vertex operator for this generator, as we would expect, we get the endomorphism AN acting on M. But when we look at the n mode of this guy, because of this shift that I mentioned before, we end up with the n+1 endomorphism of A star. Great. And in OP language, just in case you prefer that, is a free field algebra generated by these two fields and this OP. Great. And maybe I should say that in the physics literature, people up to a sign call alpha or A beta and A star gamma. And this is why it's also called the beta gamma system. Great. So we have our vertex algebra. And now let me tell you a little bit about Weyl vertex algebras. Some well-known facts. If you grab this vector, then you get a Heisenberg vector, meaning when you apply the vertex operator to it, you end up with a Heisenberg algebra. And in OPE language, you get a field that has this OPE with a minus here. So it's a scale Heisenberg. And it's well known that the Weyl vertex algebras admit a whole family of Virasoro vectors parameterized by a complex number mu. So they have conformal flow just like the free bosons. And this is what omega mu looks like. And it can be written in terms of the Heisenberg vector as well. If you're trying to study how M changes with different traces of the conformal vector, it's actually useful to write it in this way. And the corresponding Virasoro field is this one that corresponds to a choice of omega mu. You get L mu, and the OPs are this one. One can just check using the vertex algebra definition. So this tells us that when you choose omega mu to be the conformal vector for M, you end up with a vertex algebra that has central charge C mu. And I'm carefully saying vertex algebra, as I said, is not a vertex operator algebra, but it's a vertex algebra with an action of the Virasoro algebra, so some conformal structure, and this is the center charge that comes with it. Great. Okay. This new vertex algebra, once I fixed the conformal vector to be omega mu, is actually a complex graded conformal vertex algebra. It has a conformal structure for sure. And we will see that as mu takes different complex values, we do not end up in general with an integer graded thing, but we end up with a complex graded thing. this is why we're going to study and discuss complex graded vertex algebras, because the goal is to try to classify all vial vertex algebras as we move this conformal vector. Great. Here's the goal. Use the theory of complex graded conformal algebras to describe changes in the representation of this vial vertex algebra under conformal flow. Okay, good. So what are C-graded vertex algebras? Well, a vertex algebra that has a complex grading and satisfies that the vacuum is in the 0 part and the C-graded, the complex grading is compatible with the vertex algebra action is a complex graded vertex algebra. And we're going to use these bars to denote the weight of an element. And notice that the weight of an element could be 2i, I don't know, 2i plus 1/2, right? Any complex number. So it's a weird vertex algebra. If you've been working with Virasoro or affinely algebras, it's a weird vertex algebra because it has complex weights. It admits complex weights. Okay, and if on top of that, we ask that there be a conformal vector at degree 2, or a weight 2, I should say weight 2, that has the relations of the Virasoro algebra and such that L0 gives you exactly the weight operator, hence the identity, and such that L minus 1 is compatible with the derivative, then we're talking about a complex graded conformal vertex algebra. Great. We're going to define the omega space of a complex graded vertex algebra to be the vectors whose real part cannot be lowered. So omega of V is a bit of a technical definition, but we like to think of this as the space of highest weight vectors of the space, the vacuum space. Well, those, as we explained in their paper, are actually incorrect ways to call omega, because we can find situations in which the vacuum is not in omega, and we'll actually discuss one in detail. We can find situations in which people in omega are not highest weight vectors in some way. So omega is going to be all the elements in our complex graded vertex algebra, such that when you graph a U in this vertex algebra, and you do the n mode of U on V, if you ended up with something non-zero, then n was either the weight of U minus 1 and the weight of U was integer, or n was smaller than the real part of the weight of U. So in other words, if this gave you non-zero, then the real part of its weight better be smaller. No, better be bigger than the real part of the weight of V. Sorry. There we go. Okay. We're going to define, this was the definition that Leiber and Mason gave. An omega generated vertex algebra is going to be a complex graded vertex algebra such that every element can be written as a sum of things in the omega space times modes of things in V. So we're going to allow products for any integer of modes of any elements you want in V acting on someone in the omega space. And we need to be able to write any element as a linear combination of things like this. And we will show that there are actually complex graded vertex algebras that are not omega generated. So we'll show that this definition is not an automatic consequence of the definition of complex graded vertex algebra. Okay, so let's go back to our vial vertex algebras. This was one of the fields. This was the other field. This was the conformal vector. And it's, if we write the vertex operator of the conformal vector in this way, one can see that the 0 part of L mu acts as 1 minus mu times the identity on this generator, which tells us that the weight of this generator is 1 minus mu, while the 0 part of L mu acts in this generator as mu times the identity, which tells us that the weight of this guy is mu. So you can already see that there'll be things, if mu is, I don't know, 3 plus I over 2, we're going to have complex graded things, right? So hopefully you agree with me that we need to move on to the complex graded setting if we're going to study all vial vertex algebras under conformal flow. Well, great. So this is the setting. We have weight 1 minus mu for one of the generators, weight mu for another generator. And now we're going to fix mu to be 0. And maybe this is the most famous Weyl vertex algebras. Weyl vertex algebra is a C-conformal vertex algebra of center charge 2. And it has this conformal vector, which is maybe the standard conformal vector that one would take for a Weyl vertex algebra. And one can see that it ends up being Z graded or C plus graded. And that the omega space is exactly the top space, which was the span of elements of this floor. So in particular, the omega space is infinite dimensional. But as we discussed, let me just notice that maybe the case that I was making, that we need to be in the complex graded setting, is not really made in this slide. But we get that this Weyl vertex algebra of center charge 2 is an omega generated vertex algebra because every element can be written as a linear combination of things acting on the omega space, on the top space. Great. There's a lot of work that has been done on this particular Weyl vertex algebra, and maybe it's the one that's the most studied in the literature. So I'll mention a few. Andy, long time ago, showed that its Jou algebra is isomorphic to the Weyl algebra, the associative algebra with 2 generators. David and Simon proved that it admits logarithmic modules, non-semisimple in the composables. Veronica and Adamovich proved the conjecture fusion rules for the irreducibles for this Weyl vertex algebra. And more recently, Simon and Robert established the tensor category structure in a category that includes the irreducibles that Veronica and Dražen were working with, plus some indecomposable modules. So in particular, this vertex algebra admits indecomposable modules is very non-semisimple. It has non-semisimple modules. Great. But maybe I'm getting ahead of myself. For now, what I would like to say is it's an example of an omega-generated C-graded vertex algebra. Now we're going to look at another Weyl vertex algebra. So center charge 74. Hopefully I computed it correctly. So I'm fixing mu to be 3. And please, if you do this center charge and you notice that it wasn't 74, let me know. But I checked a couple times. Okay, so if I fix mu to be 3, I get a conformal vertex algebra. So I always get a complex graded conformal vertex algebra, no matter what mu is. And I claim the center charge is 74. So we're still real mu, real central charge. I could do 3 plus something just for the simplicity of computations. I'll keep it real. We'll keep it real for a second. Okay, we fix omega 3, and one can see that, okay, we lost something. There's not going to be any lower boundedness anymore. I'll show that in a second. We're still in an integer graded situation, but it's a bad integer graded situation because there'll be no lower boundedness of these components. And this follows from the fact that an element like this has weight k times 1 minus mu. 1 minus mu in this case is 1 minus 3 minus 2. So this is minus 2k. So, you know, I can graph k large enough that I will always get an element that has weight minus 2k for k large enough. So I'm going to get infinitely many things, or infinitely many negative eigenvalues that are going to show up in this decomposition, or negative weights. And the weight of this element is 3L for L greater or equal than 0. So I can also see that the weights are also unbounded above. And for a second, let's assume that the vacuum is an element in this omega space, which was the space of all vectors whose real part, whose weight cannot be lowered. Let's say it that way. We don't need to worry about real part because these things are real in this case. Okay, so I think I wrote it down to be a little clearer. So assume that the vacuum is in the omega space. This implies that if you find a U such that the nth mode of U acting on the vacuum is not 0, that must imply that n is less or equal than the weight of U minus 1. This was the definition of the omega space. But now I can easily find a counterexample to this. So I can grab U to be this generator. I can do the minus 1 mode acting on the vacuum by the axioms of vertex algebras. We know that this is the same as this element, which is non-zero. And I have that the weight of this element is minus 2. So This is my U. The weight of U minus 1 is minus 3. And I'm taking a minus 1 product, which is definitely not less or equal than minus 3. And I'm getting a non-zero thing. So I violated the definition of the omega space. So this is a little bizarre, but actually, if one analyzes the omega space of this Weyl vertex algebra carefully, one can see that its omega space ends up being 0. In particular, this is not an omega generated complex graded vertex algebra. So this is an example of a Weyl vertex algebra that is a C-graded vertex algebra, but it's not an omega generated vertex algebra. While the Weyl vertex algebra central charge 2 is an omega generated vertex algebra. Great. Any questions so far? Okay, as I said, the goal is to use the theory of complex graded conformal algebras to describe changes in the representations of the Weyl vertex algebras as we change conformal vectors. So as I claimed and didn't show you yet, the integer graded aspect is lost when we change conformal vectors. One may wonder what is the right notion of a VOA in the complex graded setting. And that's what motivates the following two definitions. So an omega generated complex graded algebra, vertex algebra, that has a well-defined degree given in this way. So as I said, if we are in an omega generated setting, every event can be written as a linear combination of things like this, where U super 0 is in the omega space. So now we're going to ask that our vertex algebra also have a well-defined degree of this form. And if we do have this degree, we're going to call that an admissible omega generated complex graded vertex algebra. Why do we call it an admissible omega generated complex graded vertex algebra? Because one can see that asking for this degree to be well defined is the same as asking for V to have this decomposition, where this is the degree 0 space that will coincide with the omega space, and this is the degree lambda space in which we'll ask that the real part of lambda be greater than 0. So in some sense, it's like admissible modules if you were thinking of n-graded modules, but in the complex setting. Great. We're going to denote by omega and this symbol. Hopefully it's clear why we're using this from this remark. This will be the category of all admissible omega generated complex graded vertex algebras. And now to the VOA definition. If we grab an admissible omega generated complex graded vertex algebra, and we ask that it also have, of course, a conformal vector that decomposes each of the complex graded spaces in the eigenspaces for L0 with finite dimensional graded components, and we will ask that the real part of the eigenvalues of L0 be greater or equal than the imaginary part of the eigenvalue for all but finally many lambdas. This may seem a little bizarre, so let me just say that again. We're going to grab an admissible omega generated complex graded vertex algebra, and we're going to ask that it have, of course, a conformal structure that decomposes our vertex algebra in finite dimensional graded components such that the real part of every eigenvalue of L0 is greater or equal than the absolute value of the imaginary part for all but finally many of the eigenvalues of L0. And if we were to go onto the real graded setting, the second condition would just become real part of lambda greater or equal than 0 for all but finally many lambdas, which is a more usual sort of lower boundedness that we would ask for modules. Great. So now we have our VOA notion in this category of complex graded vertex algebras, and we're going to use this omega VOA to denote the category of admissible omega generated complex graded VOAs. Great. Okay, here's an example that will hopefully clarify these two notions. The Weyl vertex algebra at central charge minus 13. So again, we grab the Weyl vertex algebra with omega mu in this form, it makes this element have weight 1 minus mu, and this element have weight mu. And one can see that an element of this form ends up having this weight. The sum of all the mi's that showed up with A, the sum of all the nj's that showed up with A star, plus k times 1 minus mu, where k is an integer greater than 1, plus t times mu, where t is an integer greater than 1, and mu is the complex parameter that we have fixed once we fix a conformal structure. In particular, this is just some number r plus some number s, some natural numbers, plus this. So it's clear that if we set mu to be I plus 1/2, if you think of the real part of this whole thing, the real part of the weight of any given element is going to be greater than 0, greater or equal to 0. So if we think of this as a typical V in this vertex algebra, the weight has real part greater or equal to 0 from this identity over here. Great. In particular, we have that this Weyl vertex algebra is a conformal vertex algebra of center charge -13 with conformal vector this, and it's an admissible omega generated complex graded vertex algebra. Great. Is it a VOA? Right? Like in the previous slide, we had two definitions: admissible VA and admissible VOA. Is it a VOA? Well, what we need to check is, well, many things, but one of the things that we need to check is whether the real part of lambda is greater than the imaginary part of lambda for all but finally many eigenvalues. And one can check that if you look at the weight of an element like this, then its weight is t times mu. Mu is I plus 1/2, right? So it's t plus I t over 2. In particular, the real part of the weight of this element is t over 2, which is not greater or equal than the absolute value of the imaginary part, which is t. So this eccentric Weyl vertex algebra of center charge -13 for mu I plus 1/2 is an admissible vertex algebra that's omega generated, but it's not an admissible omega generated vertex operator because it fails to satisfy this extra condition on the spectrum of L0. Great. Okay, so as I said, we would like to classify all possible complex graded vertex algebra structures on Weyl vertex algebras if I move the conformal vector. Before we do that, we're going to notice that the central charge seems to not be uniquely determined by mu. What do I mean by this? If you look at this formula, you can kind of see that if you put mu equal to 0, you get 2. And if you put mu equal to 1, you get 2. Hopefully you all agree with that. Cool. So C0 is the same as C1 is the same as 2. And actually, looking at it more carefully, you can see that the center charge, once you fix mu, is the same as the center charge once you fix 1 minus mu. So the first thing we should do is decide whether it's mu that's completely determining the structure of complex vertex algebra, or C, that's the center charge is the thing that determines the structure. So the first thing we did was prove a lemma that says that the center charge completely determines the conformal complex graded structure of this vertex algebras. Namely, we have an isomorphism that's given by spectral flow with S equal to 1, composed with conjugation with T equal to 1. From this Weyl vertex algebra to this Weyl vertex algebra, explicitly given by this formula. And we also show that if mu is not 1 minus mu, then this Weyl vertex algebras are not isomorphic as conformal vertex algebras. So really, the conformal vertex algebra structure is completely determined by the center charge. Great. And we also know we get the same center charge if we put mu or if we put 1 minus mu, and that's it. Okay, great. So now we can classify all Weyl vertex algebras under conformal flow. And this is our one of our theorems. It says, well, for mu, a complex parameter, no matter what mu is, your Weyl vertex algebra is going to be a finely strongly generated conformal complex graded vertex algebra. And you're going to get the strictest structure, which was the vertex operator algebra structure, if mu has real part between 0 and 1/2, strictly greater than 0 and lesser or equal than 1/2, and imaginary part, absolute value of the imaginary part, lesser or equal than the real part of mu, or the analogous thing for 1 minus mu. You're going to get an admissible omega generated complex graded vertex algebra, which is a bit less strict than what we asked in 1, in a slightly bigger region in the band, real part of mu between 0 and 1. And you're not going to get much structure if you are outside that band. So we're not going to get, we're still, of course, in a complex graded conformal vertex algebra situation, but we're not going to get that we have an omega generated vertex algebra if the real part of mu is greater than 1 or less than 0. So maybe here's a better representation of our theorem. We're going to get VOA structure if and only if you are in this diamond, but not in those red dots at 0 and at 1. You're going to get admissible omega generated vertex algebra structure if you are in this band, including the diamond, including the dots. And you are not going to get an omega generated vertex algebra if you're outside of this band. Moreover, we know that the omega space is just the span of the vacuum inside the band in which mu is between 0 and 1, strictly between 0 and 1. Sorry, mu and the real part of mu. I'm sorry, I should say the real part of mu is between 0 and 1, and mu is not 0 or 1. When mu is 0 or 1, we get central charge 2, and we already know that in these two little dots, the omega spaces are infinite dimensional. For one is the span of A star 0 to the J on the vacuum, and the other one will be the span of A minus 1 to the J on the vacuum. And we also have that omega is 0 outside of this bands, and this is one of the reasons why we don't get an omega generated vertex algebra outside of their band. Great. Okay, just checking how we're doing on time. Okay, and maybe a few more comments about the representation theory of this style vertex algebra. So this is the classification of all the structures that we get on this different vertex algebras if we apply conformal flow, if we deform the conformal vector. What happens to its representations? And I'll say a little bit about that. First, I would like to mention that there's a Joux algebra. There's Joux algebra machinery for complex graded vertex algebras, for admissible complex graded vertex algebras. So this is definition by Leiber and Mason that says that if you have a complex graded vertex algebra, you can define, we're going to define the floor of the weight of an element to be, or the ceiling, I'm sorry, that's what people use, I'm sorry. The ceiling of the weight of an element to be the ceiling of its real part. And we're going to define VR to be the span of all the homogeneous elements with weight, exactly weight of B minus ceiling of weight of B. And notice that with this definition, V0 is exactly the set of integer weighted vectors. So we can rewrite V in this way. And we're going to define the O space of V with this circle product. So similar to the Joux setting, except you're moving things a little bit to accommodate that when R is 0, you're going to end up with integer weighted vectors. And when R is not 0, you don't have to worry too much because this delta will kill this whole residue. And analogously to the integer graded setting, we can define the Joux algebra as the quotient of V by its O space, and it's an associative algebra with this product. And again, you may be worried about what happens if this is a complex number, but I'll just say, don't worry, because if R is not 0, so if you're not in the integer weighted vectors, this is going to die. Okay, so notice that similar to the case in which, so for instance, if you're using the Joux algebra in the super setting, you end up killing all the odd vectors. If you use the Joux algebra in a twisted setting, you also get rid of of bad things that are not integer graded. Well, very similarly, the definition of GeoAlgebras for the complex setting basically gets rid of all the bad things by collapsing them to 0. What's cool about the GeoAlgebra is that if we define the corresponding modules in these categories, so this is a definition by Lever and Mason as well, an admissible module is a module for an admissible omega-generated complex graded vertex algebra. It's just a weak module with a good grading in which the 0 component is non-zero and each component is compatible with the vertex algebra structure in this way. And what's cool about the theory of GeoAlgebras in this complex setting and the notion of admissible modules is that we have, again, a correspondence between simple admissible modules and simple AV modules in the complex setting. So admissible modules, they have a technical definition, but whatever it is, it's what you had to put here to get this correspondence between the simple AV modules and the simple admissible modules. Great, and maybe last definition, I hope, of the talk, an ordinary module for an admissible omega-generated vertex operator algebra is a weak module that admits a decomposition in eigenspaces for L0 that satisfies that each graded component is finite dimensional, and the real part of lambda is greater than 0 for all but finitely many eigenvalues. Great, so now we can state our main theorem on the rationality of admissible VOAs. And our theorem says, if you have a vertex operator algebra in the setting, so omega generated, complex graded, that satisfies that every simple admissible module is ordinary, and the GeoAlgebra is finite dimensional and semi-simple, and the conformal vector acts as a fixed constant on all irreducible AV modules, then V is rational. And this seems like a lot of conditions, but we will see that it actually applies to an interesting family of Weyl vertex algebras. Exactly the Weyl vertex algebras in that diamond, orange diamond shaped region. So what do I mean by V is rational? Well, every admissible module is completely reducible. And we use our main theorem, which actually holds in the more general complex graded setting, to show that if mu is in the orange region, well, then the GeoAlgebra of this Weyl vertex operator algebra is isomorphic to just the complex numbers, so one-dimensional, semi-simple, one-dimensional. And this Weyl vertex algebra is rational in this category, in the category of admissible VOA modules. Moreover, it only admits one simple module, and it's an admissible module that's also an ordinary module, and it's itself. So to end, after so many definitions, let me just mention that what we showed was, and Andy showed this, the GeoAlgebra of the Weyl vertex algebra central charge 2 is isomorphic to the Weyl algebra, the Weyl associative algebra, which in particular admits indecomposable modules that you can use to induce to indecomposable modules for the vertex algebra. However, when we change mu to 1/2 and we end up with central charge -1, the GeoAlgebra, and now it's a new GeoAlgebra in the complex graded setting, but that GeoAlgebra, it's actually isomorphic to just the complex numbers. It's one-dimensional, semi-simple, and you cannot use it, therefore, to induce indecomposable modules. So unlike in the situation of the free bosons, changing the conformal vector, deforming the conformal vector actually changes the representation theory of admissible modules quite drastically. That's it. Thank you so much.